Well, hello everyone, and welcome to one of the most mathematically filled videos of the year. This one, we're going to look at one-dimensional elastic collisions. So if you read the problem here, you'll notice that unlike every problem we've done up to this point, we have two unknowns at the end. Up to this point, we've collided things and looked at those collisions and analyzed them with momentum conservation exclusively. And when we've done that, we've only had one unknown. Usually either the objects stuck together, so they only had one velocity after the collision, or if there were two velocities after the collision, we had to know one of the final velocities, and then we could find the other. But here, in the special case of elastic collisions, we actually can find both final velocities. So we can know less things and find more about them because it's an elastic collision. So it's going to take a while. We're going to derive a couple of equations here that we will then use later for this one-dimensional elastic collision case. I would highly suggest you pause and go back and, as you're taking notes here, because I'm going to go rather quickly. So let's start out by analyzing this collision two ways. First of all, since it's an elastic collision, we know that kinetic energy has to be conserved by definition. So that means the initial kinetic energy of the system has to be equal to the final kinetic energy of the system. Of course, the kinetic energy of the system is the sum of the kinetic energies of the two objects. So initially we have 1/2 m1 v1i squared plus 1/2 m2 v2i squared. And then finally, we have the sum of the two kinetic energies is 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Now the 1/2s cancel out, which make the problem slightly easier. So this is what we have left when we cancel out the 1/2s. And then I am going to gather up all of the m1 terms on the left-hand side over here. See, so I've moved this one over here by subtraction. And then I'm going to gather up all of the m2s on the right-hand side, moving this one over there. You'll see why momentarily. That means, of course, that I can factor out an m1 on the left-hand terms, and I can factor out an m2 on the right-hand terms. So I get m1 times the quantity v1i squared minus v1f squared. And on the right-hand side, m2 times the quantity v2f squared minus v2i squared. Well, if this is ringing some algebra bells in your head, hopefully it is, because if you notice here, this is the difference of squares. And that means if we go to factor them, we can factor each side as a plus and a minus. If you don't believe me, or if you don't remember the difference of squares, feel free to FOIL these two things, and you'll see that you get this back. Basically, because there's a plus here and a minus here, the two inner terms end up canceling out, which is why you get the difference of squares. Now, this equation is about as broken down as we can do it, and it's got two unknowns in it, v1f and v2f. So we're going to call this equation 1, and we're going to remember it for later. Now, since this is an elastic collision, not only is kinetic energy conserved, but as in all collisions, momentum must be conserved. So we can say that the initial momentum of the system has to equal the final momentum of the system. The initial momentum of the system is, of course, the sum of the momenta of the two objects, m1 v1i plus m2 v2i. And the final momentum of the system is the sum of the two momentas, finally, after the collision, m1 v1f plus m2 v2f. Doing similar algebra, I am going to move the m1 v1f to the left-hand side to gather the m1 terms. And then I'm going to move the m2 v2i to the right-hand side to gather the m2 terms. And then I'm going to factor out an m1 on the left-hand side and factor out an m2 on the right-hand side. And again, I have an equation, a little simpler than the last one, but still a little difficult, that has two unknowns. We do not know what v1f is or v2f. So call this equation number 2. Now, one of the ways that we could then find v1f or v2f, we now have two equations and two unknowns. So in Algebra 2, you learned how to solve a system of two equations with two unknowns. One of the ways is through substitution. And so we could solve one of these equations for one of our unknowns, plug it into the other equation, and then massage. But that's going to be kind of mathematically difficult. So I'm going to show you here kind of an ingenious way that I didn't make up, certainly, that will help us solve this system of two equations with two unknowns. We are actually going to create a third equation. And we are going to do that by using the, I guess, idea of the reflexive property. And we're going to divide equation 1 by equation 2. So if this is the same as this, and if we're dividing the same thing on both sides, we can simply write it with an equal sign in between. So notice here, yes, I've divided by seemingly two different things, but remember, these two are equal, equation number 2. So I'm really dividing by the same thing, just writing it in different ways. I guess in some ways this would be like saying I'm dividing by, let's see, I'm dividing one side by 4 over 2, and I'm dividing the other side by 2. Well, those are really the same thing. They're going to give you the same result. So here I'm dividing by equivalent things. Now, watch what happens here. The masses cancel, and the V1I minus V1F cancels on the left, and the V2F minus V2I cancels on the right, and we get a much simpler looking equation. So call this equation 3. So we now have a system of 3 equations and 2 unknowns. And so if we have a system of 3 equations with 2 unknowns, we can solve this by solving one of the equations for one of the unknowns and then plugging it back into the other equation. But we don't have to use the really hard first equation for anything. So let's start out by solving equation 3 here for V2F, and we really could solve for V1F. I'm just choosing V2F to match my PowerPoint. So here we get V2F equals V1I plus V1F minus V2I. So now that we have an expression for V2F, we're going to call that equation 4, and we're going to substitute that into equation 2. So here's equation 4, here's equation 2, and we're going to put it right there. Okay, so we're going to substitute our new way of writing V2F in for V2F in equation 2. Thus eliminating it from the equation. And we now have an equation with only givens, all the initial things, and V1F. Let me check out the substitution I made there. Now, this is a great equation because it only has one unknown in it, but it's in 2 places. So here's where we do lots and lots of algebra. First thing I'm going to do is to gather up like terms inside of the big brackets. So we have a minus V2I and a minus V2I makes a minus 2 V2I. Then I'm going to factor in the M1 on the left-hand side and the M2 on the right-hand side. Got to multiply it by each of the 3 terms. Then I am going to gather all of the V1Fs on one side, and I'm going to put everything else on the other side. So here's the equation we just had. So here we go. I'm adding this one over here, and then I'm subtracting this, so there that is, and I'm adding this, so there that is. So take a second, look at the algebra. Now, I'm going to factor a V1F out of both terms on the right-hand side, and then over here I grouped these together on purpose because they are like terms in that they have a V1I that I can factor out. One more step. I'm going to solve for V1F by dividing by M1 plus M2. And I get the first of our 2 big equations. That's why I boxed this in. Notice that this allows you to find in a one-dimensional elastic collision the final velocity of one object, knowing the masses and the initial velocities. Notice you don't need to know the other final velocity to use this equation. Now, this is a velocity equation. Okay, so these are velocities here. I dropped them out during the process because of the math, but I'm putting them back in now. Okay, so these are vectors. So now that we have V1F, we have to find V2F. And we're going to do a very similar process. We're going to solve equation 3 for V1F. So there's our friendly equation 3. Solve for V1F. That's equation number 5. We're going to substitute that into equation 2 and solve for V2F. So here's equation 2. We're going to plug that right in there for V1F. Gives us this. And now we've created an equation that only has V2F as an unknown. And so here comes the fun algebra again. Here's our equation. gather like terms over here on the left. We've got a v1i and a plus v1i inside the parentheses, so that becomes 2v1i. Distribute through the m1 on the left-hand side, distribute through the m2 on the right-hand side. And now, like I did before, I'm going to gather the v2f's on one side and move everything else to the other side. So if you notice, I've added m1 v2f over here, and I've added m2 v2i right there. Factor out the v2f's on the right-hand side. Factor out the v2i's out of the two terms on the right-hand side, or left-hand side, sorry. I'm just doing that to make the equation look better. And then divide by m1 plus m2. And here is our second keeper equation. And again, this equation writes v2f, or allows you to calculate v2f, the final velocity of the second object, and it is a velocity, it's got vectors, right? So it'll have a direction associated with it, in terms of the initial conditions, the masses and the initial velocities. You don't need to know v1f. But with these two equations, you can find both of the final velocities. Right? Now, again, don't get too happy about these. These are only for one-dimensional elastic collisions. If the collision is not elastic, and remember, most collisions are in no way elastic. Right? These equations won't work. So they're very specific equations. The other thing that I learned back as an undergrad, if you want to try to memorize these, in case they pop up on a multiple choice question, if you take the first equation we had, the v1f equation, and you change every subscript from a 1 to a 2 and from a 2 to a 1, right? So for example here, if you change everything here, so you change that to a 1, you change that to a 2, a 1, a 2, a 1, a 2, a 2, a 1, a 1. You get the other equation. Take a look in your notes, if you've been taking notes, and look at those two equations and do that. So really, if you memorize one of the equations, it's very easy to get the second equation. Well, relatively easy to get the second equation. So these two big honking equations with all this math, it really is kind of a glorious amount of algebra here, and allow us to, again, have kind of another degree of freedom, if you will, in our problems, that if they're elastic, we can find both final velocities, knowing the initial conditions, not just one of them, if we only have momentum conserved, if it's not an elastic collision, if it's somewhat inelastic. We'll go on and do some examples with these a bit later, but enjoy the math, I hope.